Hello class. Today we're going to be looking at section 3.2, determining empirical and molecular formulas. The goals will be to compute the percent composition of a compound from its formula, determine the empirical formula of a compound from its percent composition, and determine the molecular formula of a compound from its empirical formula. The percent composition, the percentage by mass of each element in a compound. For example, a 10-gram sample of a compound is determined to contain 25 grams of hydrogen and 2.5 grams of hydrogen and 7.5 grams of carbon. So one would simply take the grams divided by the total mass of the sample and multiply that by 100%, and you would get its percent composition. So 2.5 grams over 10 grams times 100% is 25%. 7.5 grams divided by 10 grams times 100% is 75%. For compounds of known formula, the percent composition can also be derived from the formula mass and the atomic masses of the constituent elements. In fact, you could consider this molecule to have a total mass of 17.03 atomic mass units. Now we know the composition. We can just look at it and say, well, it's got one N and it's got three H's. So, and we know the mass of those in terms of atomic mass units. So the percent nitrogen is the 14.01 atomic mass units that represent the atomic mass of nitrogen divided by the mass of the molecule times 100% equals 82.27%. Similarly, we can look at the three hydrogens and say, well, 3 times the atomic mass units that represent the atomic mass of hydrogen divided by the mass of the molecule of 17.03 atomic mass units times 100% yields 17.76%. A compound's empirical formula can be determined from the masses of its constituent elements. So this is the step-by-step of what you do to determine a compound's empirical formula. So number one, convert element masses to moles using atomic weights. It doesn't say that here, but that's what it means by molar masses. It means using the atomic weight. So the way you convert grams to moles is that you divide by the atomic weight, as we've said before. So that's the first step. You're given the masses, convert them to moles. Now you divide, okay, so if you have elements A and B, and you can have C and D and E and whatever, but anyway, you take each element that you're given the mass of and you divide it by the atomic weight for that element to determine the moles of that element in the compound. So now you're going to have the series of moles. Element A is going to have X moles, element B is going to have Y moles, and so on. So now you look at that list of X, Y, Z, whatever, and you determine which of those is the smallest number. And then you go ahead and you divide X and Y and all the subscripts by the lowest subscript. And you make a new formula now that has at least one of its constituents has a subscript of 1, or it's normally not written when it's 1, but it has a lower subscript of 1. The other possibly has a subscript that's an integer. But if it doesn't, then you multiply the whole thing through by an integer to give the smallest whole number ratio of subscripts. Okay, so let's carry this out. A compound is determined to contain 1.71 grams of carbon and 2.87 grams of hydrogen. So the first thing we do is we take the 1.71 grams of carbon and divide it by the atomic weight of carbon, and that gives us the number of moles of carbon. And we take the 2.87 grams of hydrogen and we divide that by the atomic weight of hydrogen, and that gives us 0.0284 moles of hydrogen. So you've got these subscripts that are these fractional coefficients, fractional subscripts in the formula. So we want to clean up this formula, and so we choose the subscript that's the smallest, and we divide both subscripts by that smallest subscript. So we get 1.142 divided by 1.142. Of course, that's going to be 1. We divide 0.284 by the 0.142, boom, and that's going to be 2. And lo and behold, we get a formula that has 2 integer subscripts, 1 and 2, or CH2. And at this point, we stop. But it could have been that this was not an integer subscript, in which case we would have had another step. So let's continue. A compound is determined to contain 5.31 grams of chlorine and 8.4 grams of oxygen. After steps 1 and 2, that is, dividing by the atomic weights, the tentative formula is obtained of chlorine and oxygen. This is 0.150 and 0.525. And so you choose this because it's the smallest of the subscripts, and you divide them both by that. So this becomes 1, and this becomes 3.5. Okay, that's not what we want. What we want are integer subscripts. So we want to multiply this by a whole number, both of these by the same whole number, such that we get an integer subscripts. But we want the smallest such number that's an integer. So we look at multiplying things by 2, and sure enough, that gives us our smallest number of integer subscripts, 2 and 7. So Cl2O7 is the empirical formula for this composition, this elemental analysis that was done on the sample. So this is a flow sheet. When it says divide by the molar mass, it means divide by the atomic weight. Divide by the molar mass, it means divide by the atomic weight. So you've got mass of atoms A and mass of X atoms. So this mass we divide by the atomic weight of A. To get the moles of A, we divide this one by the atomic weight of X to get the moles of X. And then we divide by the lowest of the number of moles. We pick out which is the lowest of A or X moles, and we divide both this and this by that same lowest number, and we get a ratio of A to X atoms. And then we look at that and say, are they whole numbers? If they're not, we have to convert the ratio to the lowest set of whole numbers by multiplying everything through by a single number, and that becomes the empirical formula. A compound's empirical formula can be determined from its percent composition, because percent just means that you have so many things out of 100. So in this case, we just assume that you have a sample that's 100 grams. This is the simplest thing to do. I mean, it could be 10 grams, it could be 25 grams, but we just assume that we have 100 grams, because then the percentages become grams. So then we convert element masses to moles using the atomic weights, and then you divide each number of moles by the smallest number of moles, and then if necessary multiply by an integer to give the smallest whole number ratio of subscripts. That is superfluous. So an oxide of carbon is removed from these fermentation tanks through large copper pipes at the top. So the bacterial fermentation of grain to produce ethanol forms a gas with a percent composition of 27.29% carbon and 72.71% oxygen. What's its empirical formula? So you assume you have 100 grams of this stuff. So that percentage of carbon becomes 27.29 grams of carbon. So you divide that by the atomic weight of carbon to get the number of moles in a 100-gram sample. And similarly, with the amount of oxygen, you divide by the atomic weight of oxygen, 16, to get the number of moles of oxygen in a 100-gram sample. And then you divide by the smallest of these, which is the 2.272, and this ends up being a subscript of 1, and this is a subscript of 2, and the gas was CO2 or some multiple of CO2. And that's what we're going to talk about next, is how do you get the molecular formula from the empirical formula. Now, there are multiple ways of determining what the molar mass of a compound is, and we're not doing that yet. But let's say that you knew what the total mass of the molecule was. Well, that empirical formula implies a certain mass also. And so if you take the experimental molecular mass, divide it by the mass of the empirical formula, you know how many empirical formula units there are within the molecule. The molecular formula is then obtained by multiplying each subscript in the empirical formula by this quantity N that is calculated by this formula. Example. A compound has an empirical formula of CH2O, which has an empirical formula mass of 30 atomic mass units and a molecular mass unit of 180 atomic mass units. There are a lot of, as I said, there's a lot of ways of that people determine the molecular mass of compounds. One is freezing point depression, known as the Rast molecular weight determination. Anyway, we take that 180 mass units per molecule and divide it by the 30 mass units in the empirical formula unit, it means we've got 6 empirical formula units in a molecule. So this was the CH2O, and it turns out we need 6 of them. 180 divided by 30 is 6. And so that molecule that has that empirical formula and a molecular weight of 180 is C6H12O6. They're probably referring to glucose. But there could be other isomers that have the same molecular weight. Pardon me. And that is all we're talking about today. Thank you very much.